of two straight subbundles. So the natural question is, can we classify an decomposable algebraic vector bundle on a given projective variety? And so you want to start with the simplest possible variety, namely the complex projective space.
The German system
And then it is right?
Yes.
So let me give a bit of an overview of what is known about indecomposable vector bundle with a higher dimension projective spaces. So let's get some examples. So the first examples of indecomposable bundles, by definition, are the line bundles. So line bundles. Or any variety, but in particular, the projective space, they are always indecomposable. And then you get the tangent bundle. Tangent bundle being a simple bundle is indecomposable. Another example, so it is of rank n. Is equal to the dimension of the variety. And then it becomes difficult actually to produce indecomposable vector bundles. So the first large family, say, of such has been made by Maruyama. Actually, it produces stable, or I call stable vector bundles. I'll come back to it later, which in particular are simple and then indecomposable. So using an elementary transformation, he showed that for each rank R, that is greater or equal to the dimension of the complex projective space, there exists E, an indecomposable vector bundle of rank R. So for high rank, there are many examples, and they are produced by using the so-called elementary transformations, irrational transformation. But I won't go into the details. Yes.
The vector bundle is always over some variety.
Yes, and we just
take always projective space.
Yeah, in this lecture we just focus on projective space.
How to say the tangent bundle is in component?
Well, you can show that it is simple. For example, the space of automorphism is isomorphic to C star identity. So in particular, it does not split. Otherwise, you would have more. For any homomorphic vector bundle, you always have a C star action by the other vector fibers.
Yes.
So if you decompose in a direction, then you got a C star for each direction.
Yes.
And then
Okay.
that's one way to see it.
Thank you.
So the method to prove decomposability is by computing the chain and classes. So let's try now to produce a decomposable bundle of low rank, and this I mean below the dimension. So here you got Tango's result in 76. So by using Okay, I just say that there's a R, so for each and say greater than 3. So this incomposable vector bundle of rank n minus 1. And this is actually what is known. So what about low rank? The question is, can we produce low rank construction? And it turned out to be a very, very difficult problem. And I will try to explain the motivation to what is known as a conjecture by Hartshorne in the 70s, that the conjecture that in rank 2, there is no decomposable morphic vector bundle as soon as the dimension of the projective space is greater than 7. Let me explain why.
Sorry, I have a question about the Mayama results. Doesn't this contradict what the least result, which says that everything with large range?
If it does, it means that n is not of the n should be greater than something.
Ah, okay.
So where?
It says for every n.
Mariama?
Yeah.
Greater than 2, greater than
It's
how
fine.
much?
Or large enough then.
N should be greater than 2 for sure. Because both in this is and Mariama as well. So I think at least n greater than 2. Pay attention here. For thank you. So essentially in low rank and on CP3, there are some constructions of rank bundles over P3 that could be generalized in higher dimension in principle. First one is by using monad, that I put this on the side. And the second one is the Hartshorne correspondence. That we will now explain. So in algebraic geometry, there is a well-known correspondence between rank 1 homomorphic vector bundles, line bundles, and so-called multipliers, so that subvarieties, a formal group formed by subvarieties of codimension 1, and the Hartshorne correspondence generalizes this correspondence to codimension 2 subvarieties and put them in relation with vector bundles of rank 2. And this is how it goes. We start with E. Rank 2 holomorphic vector bundle, MTN. And you assume that you have a section so a holomorphic section of the bundle, not identically 0, and such that 0 locus of S is a codimension 2 subvariety. Let's assume that it is smooth. Codimension 2 subvariety. So locally, take a chart, a holomorphic chart in the projective space. then your line your vector bundle is trivialized, so it's U times C2. And your section is just a couple of two homomorphic maps. So you can write this as S1 and S2. But S1 and S2 are two homomorphic functions on U, or algebraic functions. And so Z intersected with this open set is the zero locus of S1 and S2. And we assume that this is smooth. The rank is fixed for the differential. It's just the intersection of S1 is equal to 0 if S2 is equal to 0, where S1, S2 is homomorphic. Okay. Then what you can show is that actually the normal bundle, you can show that by using some algebraic geometry technology to code complex, shows that the restriction of E, Z is actually the isomorphic to the normal bundle of Z in the projective space. So this is the normal bundle of Z inside the projective space. So it's the quotient of the bundle of the projective space by the tangent bundle of Z. And if I take the second exterior power, the top power for this rank 2 bundle, I obtain that this is a line bundle. So the second exterior power is shifted to Z. It's isomorphic to the second power of N. So that's a line bundle. A one-point vector bundle. And so in particular, this shows that the top exterior power of this normal bundle extends as a line bundle to the whole projective space. So there is an obstruction for this picture to be true if you consider a Cone-dimension 2 subvariety, and you want this to be described as a zero locus of the section of a holomorphic bundle, then it has to satisfy this constraint. So the Hartshorne correspondence tells you that this is the only constraint. So if you take a Cone-dimension 2 subvariety in the projective space, and you assume that the top external power of its normal bundle extends holomorphically on the whole projective space, then there exists a vector bundle rank 2, a section such that the zero locus of the section is your Cone-dimension 2 subvariety. So this is called the Hartshorne correspondence. Let's start here. Conversely, Hartshorne tells you
what is particular about the rank 2 in this case?
That's a good question. I suspect definitely aware of the argument fails in my mind, but it doesn't work in general, right? There are other expressions that should come in, but I have never seen that written down. So that's one thing. The second is that it's not in general so easy to check this condition already. So maybe it's why. So you can always go in one direction easily, right? It's not so clear.
Everything makes sense right up to the statement.
Sorry?
Everything up to the statement is like it's fine.
Oh, until here it's fine.
Yeah.
But it's the converse.
Yeah.
The converse is not clear. So conversely, if Z, say, is a smooth fundamental piece of variety, of dimension 2, that's an M, that's a 2, and if star holds, then there exists E upon 2 homomorphic, and there exists a section substance Z like this. So this problem of producing, and moreover, back to the problem. Z is a complete intersection. Complete intersection, meaning that it is the intersection of two hypersurfaces in the projective space, if only if E is split. So it means that E decomposes as the sum of two line bundles. L1 plus L2, where Li is a line bundle. Line vector bundle. Okay, we want this local picture to be global, and this arises precisely when those two sections, S1 and Si, S1 and S2 exist globally. We give you this split on the whole projective space. Okay? So the problem of finding low-rank vector bundles, in particular vector bundles of rank 2, is closely related to the problem of finding codimension pieces of varieties that have a specific geometric structure. There should not be complete intersections. So that's a very difficult problem. And this Hartshorne correspondence has been used successfully on the three-dimensional projective space to actually produce many examples of rank 2 vector bundles that are not split. But in higher dimension, turned out to be much more complicated. And let's take one last result. So using this Hartshorne correspondence, what Owens and Antwerp managed to prove on P4 by Owens. In 33. So there exists an embedding of a specific surface, an abelian surface in CP4. And then an abelian surface. And in particular, this shows that you can produce the Hartshorne and find that there exists E around 2 indecomposable vector bundle on E4. So for those who know a little bit about topology of algebraic varieties, you see that this is a highly non-trivial fact because let's just several, for example, you see that the fundamental group is not trivial, there it is. So there are a lot of obstructions to this, and actually Hartshorne tells you that Z is not a complete intersection. This is very difficult to do. And this is exactly, well, in my knowledge, this is the state of the art today, about construction of rank 2 in decomposable vector bundles on the projective space. There is no other constructions, at least in characteristic 0. There are some constructions in positive characteristics on P5, and the story stops here. So for other considerations as well, this led to the following conjecture by Hartshorne. This is a specific case of the wider Hartshorne conjecture about subvarieties in the projective space. So if you take dimension 2 for vector bundle, it is the following: for L and vector equals to 7, there is no rank 2 holomorphic in the composable vector bundle on CPL. So as you can see, that's a null conjecture. Actually, been no progress toward potential constructions. Any question at that stage? Maybe I could just say, without writing it, that it's closely related to another problem called the Borel figure problem about smoothing cycles in a smooth projective variety. And for this problem, there are positive results, particularly a result by Collard and Voisin very recently. And this led to a rational version of Borel figures problem. And very recently, Voisin and Olivier Benoit have shown that a positive answer to Borel figures problem is not compatible with a positive answer to Hartshorne's prediction, meaning that if Hartshorne is right, then the rational version of Borel figure problem has a negative answer. So there are two somehow conjectures or problems, and they can't be simultaneously correct. So one conjecture has to be wrong. And they also prove a symplectic version of Borel figures problem for the rationals, and argue that this then shows that Hartshorne's conjecture should be wrong. But I'm happy to discuss that.
Can I ask you something? So it says that any codimension 2 subvariety in PL that is not a complete intersection, the normal bundle can never come from an ambient bundle. This is an equivalent formulation.
No. Thanks for asking the question. So this condition for Hartshorne sphere is always satisfied from n is equal to 6. This is a defined bar. Also, I think. So automatically, in high dimension, rank 2 algebraic bundle corresponds to codimension 2 subvarieties. And there is a conjecture of Hartshorne on complete intersection in the projective space. If you translate this for vector bundles, it gives you this conjecture. So it says that if you take a codimension 2 subvariety in the projective space, from dimension 7, it must be a complete intersection. That's one combination.
Where the normal bundle extends.
And that's automatic from n is equal to 7. From n is equal to 6. It's okay. It's not a constraint anymore.
And what happened is with the twisted cubic P3 also like this. So the very first example of an incomplete intersection with P3, then when phase is obviously the normal bundle does not extend.
I don't know. I don't know. Yeah, that's the first thing you mentioned. Okay, so let me present a new approach to the question. So no conjecture solved today during the lecture, unfortunately, but it's a new problem and some partial reasons. So the starting point is an observation. First, I should define stability. So what I'm going to explain briefly is that there is some kind of a big space that parameterizes all those wrong two vector bundles that we are looking for in abstract space. And we define it requires stability. So let's assume, although we know what this is fine, and for those who don't mention implementation, we're going to explain everything with C1 all. Whatever that means. So in particular, the various stability notions agree. And I will say that my vector bundle E is stable. It is a homomorphic vector bundle. And I want to compare a measure of positivity of this vector bundle for its subbundles, but I've got to consider slightly more general subobjects, vector bundles with singularities somehow. So it's for all coherent subsheaves. With rank 50 between 0 and 1 E, the slope of f for all f such that we have the slope of f is strictly less than the slope of E, where as I said, the slope measures kind of positivity. It's defined as an intersection number, first and inverse of E, that's the topological invariant, with a right plane section divided by the rank. And the upshot is that with this notion, you can bound the set of bundles that you want to parameterize with some fixed topological invariant. And because you can bound it, then you can produce a space that parameterizes all isomorphism classes of vector bundles with fixed topological invariants. So there exists, and this goes back to the work of Antwerp, Mariana, Disseker, Gauthier, Simpson, and others, M, which is a moduli space. For rank 2 stable vector bundles, holomorphic vector bundles on the project space with fixed topological invariants, namely the Chern classes, fixed C5, C1 and C2 because we are in rank 2. And those are the Chern numbers, Chern classes. Okay, so that's a kind of a master space that parameterizes for fixed topology all the rank 2 holomorphic vector bundles. So it parameterizes in the sense that its points are in bijection with isomorphism classes of those holomorphic vector bundles. And it's also carries information about how they vary in families.
So this space might be n.
Exactly.
What's the dimension of the Lambda space?
Sorry?
What's the dimension of the Lambda space?
I don't know. Computing the expected dimension is already not so easy. You know, so the real the actual dimension requires to develop the deformation theory, as we'll see in minutes. But unless you are on, say, CP2 or CP3, a lot of results in general.
But I mean, if the conjecture is true, then it should be like zero dimensional, right?
There should be none.
Yeah.
It should be empty.
I mean,
Because the stable bundle is always indecomposable.
okay.
That's a good point. This implies that's a good point. This implies stability, implies simplicity, and this implies indecomposable. Thank you for asking. But never mind. What is known is that this space in general is a quasi-projective scheme. And we can consider the underlying variety. So it's an open variety in some projective space of higher dimension. Some open variety of a larger projective space is quasi-projective scheme. And because it's not compact, this causes some issues. So we might want to consider compactification, and there is a so-called modular compactification. So you can compactify this in such a way that the points that you add to the boundary correspond to a parameter space for a larger class of objects, which are semi-stable sheaves. So you gotta go to coherent sheaves. And because I asked C1 to be odd, those are the stable sheaves. So there exists a so-called modular compactification. Parameterized is instead of just coherent bundles, I have to consider coherent sheaves, concentric sheaves. So its boundary point corresponds to stable concentric sheaves. Sheaves are 1, 2. And shell numbers 1, 2. And here, I'm going to add 0 because for those sheaves, the way you construct the topological invariants, it's not always true that the higher topological invariants vanish. It could be on 0, so it's required here that they have the same as the one that we consider.
Very practical.
Yes.
Or this is like homological.
No, you could have 1, 2 torsion-free sheaves. You could have higher Chern classes because the way you build those, for vector bundles, you use, for example, Chern-based theory or botanics construction. So it's automatic that below that after the rank it vanishes. But when you consider a sheaf, you take a resolution, and then you use those properties, or you go to the bottom good and then higher Chern classes of it. It's not for free. Okay, so where do I want to go? What is the observation? And that's coming from old work from 2011. So the complex projective space is a toric variety. This is where toric comes in. Toric variety, which means that there exists a torus action, regular action of a multiplicative torus, so it's just C star to the n that acts in a regular fashion over CPN. CPN, explicitly to take T torus and Zn a point in a projective space. Let's consider T times this point. And I have a n coordinates in my torus, so I'm going to pick 0, and then consider 0, 1, 2, 1, etc. So this action actually induces a regular action on the normalized space by pulling back the vector bundles into the torus action. And this action extends over the compactification in a natural way. It's actually also true at the level of skills. This was proved by Cole in 2011, following the work and the suggestions of Kriashko on the 90s. Theorem. T regularly on M bar by Ajax. And preserves the action preserves the locus corresponding to vector bundles. And the nice thing here is that this is a compact, say, you can consider the projective variety behind this, so that's compact. That's a regular action of the suburb group. So they are fixed points. That's a general Borel fixed point theorem. So by Borel fixed point theorem, there are fixed points. Fixed points in bar for the T action. So let's assume now that M is non-empty. Get back to this. Our initial problem is whether M is empty or not. In dimension 2 and dimension 3, we got many examples where it's not empty, and the geometry of these spaces have been intensively studied. So assume that there exists stable, so in particular indecomposable rank 2 vector bundle in M, then by Borel, there are fixed points in the orbit closure. Points, say F of this one, say this one, F, and the torus section in the orbit closure of E. And by general theory, you can actually assume that there is a degeneration to this fixed point. Result of Ken, there is a one parameter subgroup. One parameter subgroup. That sends the class of E to the class of F. And we can actually reverse the construction and see E as a small perturbation of F, a small deformation. And we can actually lift everything to the code scheme and obtain a flat family. Such that the limit of 0 of S times E is F, which implies that there is actually a flat family, flat over C, in tilde. So it's a family of rank 2 conjunction-free sheaves on a projective space that varies somehow continuously, that's what flatness stands for, and such that at S is equal to 0, we have this fixed point, this special sheaf F, and for S non-zero, our sheaves are all isomorphic to E. For S non-zero. that being a fixed point, this sheaf has an extra structure. This is what is called a toric sheaf. So it's not totally straightforward. But a little bit of work can show that there exists the following structure. So that's the toric sheaf. So, toric function free. Meaning that there exists an isomorphism between the pullback of F under the torus action and the pullback of F under the projection, where alpha is the multiplication of the torus here. So it's the torus action, and pi 2 is simply the projection on a second factor. And this satisfies some cocycle condition that mimic the group actions on spaces. It has an extra structure, and the short the observation is then the following: if there is a counterexample of Hartshorne's conjecture that is stable, and there's a good reason to believe that the Hartshorne's conjecture, if it's wrong for stable bundles. So if you can find a counterexample, then we can find one that is a small deformation of the toric sheaf. If there are counterexamples, we know where they're going to lie. Or maybe there are other examples, but at least if there is one, we know that we are going to reach another one, maybe that's considering small perturbations or small deformations of toric sheaves that run through. So we know where. And so the program then is the following.
You don't know what this is connected?
No, not for this. No, because I'm not considering any fixed point. I consider a fixed point that is in the orbit closure. So that's fine. So the problem is the following. First, construct stable run 2 toric sheaves, toric sheaves with the right chain numbers, the right topology. So we want those classes we want the higher chain classes to vanish, and so on. And we also want the classes to satisfy some other topological obstructions, known as Schwarzenberger constraints, and even more constraints coming from indecompatibility. And then the second is smooth them out or deform them. From those to locally free sheaves of hectaponters. And what I'd like to explain in the last 10 minutes is that, well, for step 1, it's done now, it works, and there is no machinery that enables to prescribe chain classes for any toric sheaves on the projective space, and part of the reduced extent of the toric varieties, which is already a result in itself because it shows you precisely what are the chain classes for non-empty moduli space of Hartshorne free sheaves. Because by the same argument, if you have a non-empty modular space of Hartshorne free sheaves with fixed chain numbers, then there is a fixed point. So you can answer to the following question: is this modular space non-empty? If you consider modular space of Hartshorne free sheaves, and we'll just have to check whether you can reach a toric point in this modular space with the right chain class. So, say we have 3 prescribing chain classes. by sheaves. Okay, so let's start with a simpler, say, a baby case. Some of those sheaves are maybe not located free, but they are so-called reflexive. So I start with this so-called reflexive sheaves. The reflexive sheaves are like mildly singular vector bundles. And in particular, they are normal, which means that the sections extend automatically across codimension 2 subvarieties. So E is a toric reflexive sheaf. Is toric reflexive. Oh, I did not give the definition. Reflexive means that it's isomorphic from the evaluation map. It's double dual. It is not automatic for sheaves. Then it is normal. So then sections of E over U minus isomorphic sections of U minus Z of E, where Z is of codimension vector equal to 2. Codimension of Z. So to describe a toric sheaf, I draw a picture. It's enough to describe the space of sections away from codimension set of dimension greater than 2. But because of equivariance and because again is toric, it's enough to check how section extends across those invariant divisors. So if you draw P2, and the same picture with P2 and yeah. So this is P2. I have 3 divisors, so those are given by the vanishing locus of my homogeneous coordinates. So they cut out codimension 1 subvarieties. This is 2 is equal to 0, and then 1 is equal to 0. And to describe the sheaf, I just have to understand how sections that are defined on the dense open orbit of the torus extend or not. So this is isomorphic to the torus. I have to understand how sections defined on this torus extend across those 3 divisors, 3 codimension 1 subvarieties. So here I've got a special point in the torus, it's 1. And my sheaf over this point is just isomorphic to C2. So I've got a copy of C2 here. So at this point, because of equivariance over the torus, the sheaf is isomorphic to this copy of C2 times the torus. Plus some data coming from the representation of the equivalent structure. And so to describe my sheaf, I have to know whether sections extend or not across this divisor. So what's going to happen is that this is related to the weight of the transverse action. So for each divisor, I have a weight, say an integer, and I have a line of sections that will extend as soon as the weight is bigger than a threshold, and then all sections will extend at a given threshold and up to normalization. This is all what I need to describe the sheaf. So for each divisor, I've got a weight corresponding to the transverse action and a line that corresponds to part of the section that will extend. So this is clear description of toric reflexive sheaves. It has been formalized then by Perling in a more general setting of torsion-free sheaves. So E is entirely encoded by a normalization by those integers and those lines, and that's true in any dimension for the polygon space. So the i's are integers, and the lines here. So the lines. And this is useful here. and pairing them for concentric sheaves. So the term classes that I want to prescribe after computation can show that they are precisely the symmetric elementary polynomial in the AI. This implies that the CI, the term classes, those invariants are symmetric elementary functions in the AIs, and in particular, with the normalization that I'm hiding here, it shows that C3 is positive and vanishes precisely when E is locally free, when E is a vector number. This result was known on P3, back to Hartshorne. And for toric sheaves, it's actually true in any dimension at 1, 2. So this implies that the third term class is positive with equality if and only if V is a vector number. And with a little bit more work, you can actually show that it is a vector bundle that is equivalent, then it splits and it has no deformation. So those will never produce counterexamples. Whereas if C3 is strictly positive, then when you deform, C3 remains strictly positive. So it can't be the third term class of a vector bundle. So those will never deform to counterexamples. So reflexive toric will never produce counterexamples. Never produce counterexamples. So you really have to go to the torsion-free case, a much more general case. And in a torsion-free case, you have a canonical injection coming from the evaluation map. It's not an isomorphism anymore. Is torsion-free, whatever it means, and there is an injection, this is the evaluation map, into its double dual. This one is reflexive and toric. So I know how to compute the term classes for this one, and I want to derive from this information the term classes for the general case. It's not so straightforward to do it in general, so there is a little tool that can help. And actually, it's working for any injection between toric sheaves, torsion-free toric sheaves of the same rank on any smooth projective variety, toric variety. Just get it here. So this injection factorizes through elementary injections. So the terminology was chosen because of Mariana's elementary transformations. Actually, I chose the terminology and then I realized that Mariana had elementary transformation. It was kind of like terminology. So what are the elementary injections? And then I stop. So what does that mean? This factorizes means there exists a sequence for E0, E1, E2, maybe not unique, E double dual, such that each AI plus 1 is elementary, which means that there is a quotient of both are toric and torsion-free. Toric and everything is equivalent. Toric, torsion-free. And then there is a quotient its injection. And the quotient is going to be as simple as possible. So Qi is a torsion sheaf and it's pure. So it's 0 away from an irreducible subvariety. And this irreducible variety is actually, well, it's irreducible, so it's something to mention. So with irreducible support, say B, and the restriction of the sheaf to its support is around 1. As simple as one could hope for. So you can decompose this injection into simpler injections, but for those injections, it's actually easy to compute the Chern numbers. So at each step, you can compute the contribution of the new injections to compute your Chern classes. And if you go the other way around to actually prescribe Chern classes, the idea is then to follow this scheme and start with a toric reflexive sheaf that is stable, that's easy to produce with prescribed Chern classes. And then step by step, you hit the higher Chern classes that you want to get rid of by choosing in a smart way those irregular transformations or injections. And in the end, you can actually show that you can prescribe infinite families of rank 2 torsion-free stable sheaves, stable sheaves on any dimensional complex quadratic space with the right Chern classes. Nice.